This video is Module 4, Physical Layer, for the Introduction to Networks course, version 7.02 for the Cisco Networking Academy. In this module, we're going to be looking at the physical layer, the purpose of the physical layer, the characteristics. We're going to look at copper cabling, UTP cabling, fiber optic cabling, and finally, wireless media. So what is the purpose of the physical layer? The physical layer allows us to send ones and zeros from one device to another. So before any network communication can occur or take place, a physical connection to a local network must be established, or a wireless connection must be established. So it can be wired or wireless, but a connection does need to take place for those bits to be transferred. So a network interface card connects a device to the network, and some devices have one NIC, and others might have multiple NICs. They might have a wired and a wireless, or some type of combination. Usually servers are going to have multiple NICs in them, or network interface cards, and some gaming desktops will have a wired connection, and then they will also have a wireless connection as well. When we look at the physical layer, it transports bits across the network medium. It accepts a complete frame from the data link layer, and we're talking about the OSI. It encodes it as a series of signals that are transmitted to the local media. And this is the last step in the encapsulation process. And then the next device in the path on the destination, it receives the bits, and then it re-encapsulates the frame and decides what to do with it once it starts reading the information. The physical layer characteristics, when we look at those are in the OSI model. Those are at the, we call these the bottom, but they are the layer 1. So layer 1. Some of the components of the physical layer, we have physical components, we have encoding, and we have signaling. They address those three functional areas. And the physical components are the hardware devices, the media, or other connectors that transmit the signals that represent the bits. When we encode, it converts the stream of bits into a format that's recognized by the next device in the network path. The coding provides predictable patterns that can be recognized by the next device. In other words, we increase the signal to go above a certain voltage so that we know that the bit is on. So the bit is on and we get a 1. If the voltage drops, we get if it drops below a certain level, we get a 0 bit. The signaling method is how the bits of ones and zeros, or values of ones and zeros, are represented on the physical medium. The method of signaling will vary based upon the type of medium. Light pulses will go across a fiber optic cable. Wireless will look more like this when we look at it on a graphic. They will look more like this, wavelengths. And digital will be more boxy. The term bandwidth is the capacity at which a medium can carry data. I like to think of bandwidth as how many lanes of traffic you have on a highway. So digital bandwidth measures the amount of data that can flow from one place to another. So if I only have 2 lanes of traffic, or 2 lanes for cars to drive, I'm going to have a smaller bandwidth if I had 8 lanes of traffic and I could put 8 cars down the highway at the same time, I'm going to have a larger bandwidth. And when we measure this, we talk about bits per second, or BPS, and that's 1 bits per second. That's fundamentally the base unit of bandwidth. And then we go up from there: kilobits, megabits, gigabits, and terabits. Some other terms that you want to be familiar with are latency. That's the amount of time, including any delays, for the data to travel from one given point to another. The throughput is the measure of the transfer of bits across the medium. And goodput is the measure of usable data that's transferred over a given period of time. So the throughput minus any traffic overhead will get you the goodput. With copper cabling, we have some characteristics of copper cabling. It's the most common type that's being used in networks today in the year 2026. It is inexpensive compared to other networking mediums. It's easy to install. It has low resistance to electrical current flow, but it does have some limitations. Attenuation is another word that you want to be familiar with. That just means that the longer the electrical signal travels across the medium, the weaker the signal gets. The electrical signal is susceptible, or it's prone to interference from 2 different types of sources that can disrupt or distort the data signals: electromagnetic interference, or EMI, and radio frequency interference, or RFI. And that's what we call back crosstalk. Mitigation is the strict adherence to cable length limits, and that will mitigate attenuation. So if we know a copper cable will only allow for a certain distance before the attenuation breaks down the signal, we only put copper cable in for that length. Some kinds of copper cabling can mitigate EMI and RFI by using metallic shielding and grounding. And then some types of copper cabling mitigate crosstalk by twisting opposing circuit pair wires together. Here we have some visual representation. This is an unshielded twisted pair cable. It's the most inexpensive, or it's the least expensive of all the copper cabling. The shielded twisted pair uses extra shielding. You can see here the wires are wrapped around each other the same way they are for the unshielded twisted pair. But here we have metallic wrapping that goes around, and we also have some extra plastic that's in the center to help give it some stability. But that extra metal right there that's wrapped around will eliminate, or it doesn't eliminate, but it will reduce some of the EMI and RFI. And then on a coax cable, we have the main cable in the middle. You have some plastic sheathing there. Then we have a metal wrapping, and then some copper cross metal, and then we have plastic covering. When we look at unshielded twisted pair, that's the most common networking medium. It is terminated with the RJ45 connectors. It connects intermediary devices together. And the key characteristics of it are the outer jacket protects the copper wires from physical damage. This is the outer jacket here. The twisted pairs protect the signal from interference. You'll see that the pairs are twisted together. And the color coding plastic insulation isolates the wires from each other. So you'll see that there's a little bit piece of copper wire inside. So we have plastic coating here, and then we have this plastic coating here. But by putting this plastic coating, and then by wrapping them together, and then by color coding them, that lets us know what the wire does, and it also protects it, and the wrapping cuts down on, it helps us with the attenuation. With shielded twisted pair, we still have the little small copper wires in the middle. We have the plastic sheathing. We have them wrapped around each other. And then we also have them color-coded. But additionally, we put metal or some type of, usually metallic, covering around the bundle of wires, which will cut down on the noise. So it's more expensive than UTP because it does require extra materials. It is harder to install than UTP because it's got extra material to it, so it's harder to move around corners. It is terminated with the RJ45 connectors, which is the same as the UTP, and it does interconnect hosts with intermediary network devices. Some of the key characteristics is the outer jacket protects the copper wires, the braided or foil shield provides EMI, RFI protection, and the foil shield for each wires provides EMI, an extra layer of protection. And then the color-coded plastic insulation isolates the wires from each other and then identifies what the pair does. And then finally, we look at coax cable. The outer cable of a coax cable prevents minor physical damage, and a woven copper braid or metallic foil, that's what you see right there that I'm marking, acts as the second wire in the circuit, and it also acts as a shield for the conductor. A layer of flexible plastic insulation wraps around the inner copper core. And there are different types of connectors that we use, the B and C, the N-type, and the F-type. Now let's take a closer look at UTP cabling. UTP has 4 pairs of color-coded copper wires that are twisted together. They are put inside of a flexible plastic sheathing, and no extra shielding is used. And that makes it cheaper, but it also makes it more susceptible to interference. So it relies on some properties to limit crosstalk though. Cancellation just means that each wire in a pair of wires uses opposite polarity. One wire is negative, the other wire is positive. And this goes back to the early days of electricity. Scientists discovered that if you cross wires together that are opposite polarities, you will cut down on the crosstalk and you will allow for a longer distance for that signal to travel. So the variation in twist per foot in each wire is twisted with a different amount, which helps prevent the crosstalk among the wires in the cable. We use the TIA EIA 568A and 568B standards. One has one direction, one has the other. But that standard sets the cable lengths, the cable types, the connectors, the termination, and the testing methods. And you're going to see different categories. in the year 2026, you don't see a lot of category 3 anymore, but there is some still out in the world that's being used. You're usually going to see 5E, 6, 7, and maybe even higher, but most common is going to be the 6 at this point. The RJ45 connectors, you have this plastic housing, you have these little metallic pins here, and you will also have a protective sheath that goes around. These are the sockets, so this male part here goes into the female connector there. This is a socket of the inside, so what happens is this wire plugs into here, and then once it plugs into here, the wires then come in and get connected like this, and they get punched down, and you use a punch down tool to do that. A poorly terminated UTP cable, here you'll see the sheathing is not all the way up in the protective housing. So you'll want to make sure that if you're putting an end cap on, what you'll do is you'll cut these wires and you'll put them up into the housing, and they should be lined up underneath so that when you crimp it down, these teeth or these little metallic teeth here will get pushed down into the wires for the connectors, and this little plastic piece here will bite down on the plastic sheathing and hold it in place. I mentioned earlier the T568A or T568B. There's two standards. One, this is the A, this is the B. Both ends on these, you can create a straight through. That just means that both ends are either A or B, and you're going to use that instance in a hosted network device. If you do a crossover cable, that means that one end is the A and the other end is the B, which means you're crossing over the cables or you're crossing the signal over. And we use those for host-to-host, switch-to-switch, or router-to-router. And then we have a rollover cable, and that's usually a Cisco proprietary, but we also use a host serial port to router or switch console port using some type of adapter, but a rollover cable is a little bit different. Next, we're going to look at fiber optic cabling. It's not as common as UTP because it is more expensive. However, it is ideal for some networking scenarios. It transmits data over long distances with a higher bandwidth than other types of networking media. It's also less susceptible to attenuation, and it's completely immune to EMI and RFI. It's made of flexible, extremely thin strands of very pure glass, and it uses a laser or an LED light to encode bits of information as pulses of light. And the fiber optic cable acts as a waveguide to transmit the light between the two ends with minimal signal loss. The two types of fiber that we're going to look at are single mode fiber. Single mode fiber just means the light gets sent down the light path. It's very small core. It uses expensive lasers, but it does have a long distance application. And then the multi-mode fiber allows for multiple paths of light to be sent down the cable. It does have a larger core. It uses less expensive LEDs. It transmits at different angles so you can have multiple paths of light at the same time. You're going to get up to 10 gigabits over 550 meters. Fiber optic cabling is now being used in 4 primary types of industry. Enterprise networks use it for backbone cabling for applications and connecting infrastructure together. You have fiber to home, or FTTH. That's used to provide always-on broadband services to homes and small businesses. We also use it for long-haul networks. That's used by service providers to connect countries and cities together. And then we have the submarine cable networks, or the underwater. They will put those under the oceans. Those are used to provide reliable, high-speed, high-capacity solutions capable of surviving in harsh undersea environments up to transoceanic distances. The fiber optic connectors that we're going to be concerned with in this course are straight tip connectors, Lucent connectors, subscriber connectors, or duplex multi-mode LC connectors. The fiber patch cords, you'll have SC patch cords, SM patch cords, MM patch cords, and SM patch cords. A yellow jacket is for single mode. So yellow jacket is for single mode, and orange or aqua is for multi-mode. When we compare fiber versus copper, optical fiber is primarily used as backbone cabling for high traffic, point-to-point connections between distribution facilities and connecting buildings together in multi-building campuses. So if we're going to connect buildings together in campuses, we use fiber optics. If we're inside the building and we're in the same room, we're most likely going to be using UTP, or unshielded twisted pair. So the bandwidth supported for unshielded twisted pair is 10 megabits up to 10 gigabits. Fiber optic gives us 10 megabits up to 100 gigabits. The distance for UTP is relatively short, up to about 100 meters, but we can go up to 100,000 meters with fiber. Immunity EMI and RFI is low. Immunity to electrical hazards is low, but the cost is low with UTP. The installation skills required is low with UTP, and safety precautions are fairly low with UTP as well. Fiber optic, it's completely immune to EMI. It's completely immune to electrical hazards, but it is very expensive. It does take some extra training and extra skills to install, and the safety precautions are a lot more because if you break the wire and where you're laying the wire, you have to make sure it's not cut. It's just there's a lot more safety precautions that need to be taken and are put in place. Now we're going to take a look at wireless media. Wireless media carries electromagnetic signals representing binary digits using radio or microwave frequencies, and it provides the greatest mobility option of the connections. So wireless connection numbers continue to increase because of the flexibility. It allows us to have different coverage area. However, that effective coverage can be impacted by the physical characteristics of the deployment location. In other words, if I have a building that's made of all metal, I'm not going to get as great of coverage if I have a building that's got a more open floor plan and made of material that's more porous or open. So interference with wireless is also susceptible, or wireless is susceptible to interference, and it can be disrupted by a lot of different common devices. Also with security, wireless communications require no access to a physical strand of media, so anyone can see access to that transmission. So if you are transmitting wireless, anybody can see those signals with a proper receiver, and unless it's encrypted, they're going to be able to see that data in the open, and even if it is encrypted, then they could try to break the encryption. And also shared medium, or lastly, we'll look at shared medium. Wireless LANs operate in half duplex, which means only one device can send or receive at a time, and many users accessing the wireless LAN simultaneously can reduce the bandwidth for all the users. The IEEE sets standards for wireless data communications, and they cover both data link and physical layers. In each of those standards, the physical layer specifications do determine that the data to radio signal encoding methods, what they are, the frequency and power of the transmission, the signal reception and the decoding requirements, and the antenna design and construction. And some of the wireless standards that we will look at or take that are included are Wi-Fi. Those are set by IEEE. That's the 802.11. Bluetooth, which is 802.15. WiMAX, which is 802.16, and Zigbee, which is 802.15.4. And I will just make a note here at the end. You do need to be familiar with these different standards, the 802.11, 15, 16. You need to know what they are. So on the final exam, you're probably going to see those again on a question. In general, a wireless LAN requires a wireless access point. You can either call it a WAP or an AP. Most commonly, you're going to hear the term AP or access point. It concentrates wireless signals from the users and connects to the existing copper-based network infrastructure. And you're also going to need to have a wireless NIC adapter on your device, which provides connection. And the number of wireless standards, when purchasing wireless equipment, you need to ensure that you have the proper capability and interoperability between your device and the wireless that you're going to be connecting to. And network administrators must develop and apply stringent security policies and processes to protect the wireless LANs from unauthorized access and damage. Wrapping up this module, what did we learn? We learned that network communications, before any network communications can occur or happen, a physical connection to a local network needs to take place by either wired or wireless. The physical layer consists of electronic circuitry, media, and connectors. The physical layer standards address three functional areas: physical components, encoding, and signaling. There's three different types of copper cabling: UDP, SDP, and coax. UTP cabling is the cheapest. It's governed by the TIA EIA connections and by the IEEE. The main type of cables that are obtained by using specific wiring are Ethernet straight through and Ethernet crossover. We learned that optical fiber cable transmits data over long distances, that there's 4 types of fiber optic connectors. We learned that the fiber optic patch cords include multi-mode, single mode. We also learned that wireless media can carry electromagnetic signals that represent the binary digits of data using radio or microwave frequency. However, wireless does have some limitations. It can be subjected to security issues, interference, and problems that occur with any shared medium. And we also looked at the standards, the 802.11.15.16.15.4, and that wireless LAN requires a wireless AP and a wireless NIC adapter. And finally, here are the new terms and the commands that we learned in this module. I will leave this up for a few seconds. You can pause the video here if you want to get a screenshot. And thank you for watching, and I hope you have a great day.